Hey you guys, Lissandro here, and today I'm gonna do a whiteboard tutorial. I know I haven't done these in quite a while because I've been reevaluating some of the methods I use to create videos. Whether I use something more graphical, visually appealing, or I stick to the simple method of just kind of drawing out explanations and things like that. But I thought I would do a combination of both in reality. So today, what I'm going to talk about is something in particular that's in a lot of electronic devices and I guess other devices. And what this is what you call a heat sink. Okay. If you're wondering how heat sinks look like, they mostly look like this. Okay. So heat sinks, they're mainly meant to dissipate heat. Okay, they're meant to uh, dissipate heat to mainly keep something a lot cooler. Okay, all right. So, why would you want to keep something cool? And mainly, these are used for, let's say, for example, your computer. It has, they have heat sinks. Also, heat sinks for voltage regulators, or heat sinks for industrial motors. Okay, those are what heat sinks are for. But the thing is, have you ever wondered why exactly heat sinks look like this instead of this? Okay, the reason why is because it's mainly because of what they call surface area. Okay, surface area. Okay, and the reason why surface area is very important is because mainly there are a variety of factors of which determines how well heat travels. One of those factors is um, your temperature difference, and delta T. Um, that's your temperature. Your temperature difference. Okay, your temperature difference. Basically, for example, if you have for example, let's say that you have aluminum plate. Okay, and on one side it's super cool, and on the other side is hot. Okay, then it's more likely that that heat is going to travel uh, from the hotter side to the cooler side much more easily rather than if you had a smaller temperature difference that in which for example aluminum plate has a certain amount of heat and below it has a certain amount of heat, not that much different from the top portion. It's not gonna travel as heat's not gonna travel as efficiently as it would on a temperature difference where something's hot or something is cold, or it doesn't even necessarily have to be cold. You could have something that's 100 degrees, and you could have an object that's like about 1,000 degrees, and heat would rush to the coolest part, which would be the object that's 100 degrees. Okay, and the next thing is the medium. Okay, the medium. Okay, yeah, medium. Okay, so the medium is very important because it determines how it determines not only how but what is going to be traveling through. And there's four different mediums in terms of matter that determines how heat is going to travel, whether it's through a solid, which is direct contact. Okay, and that's called conduction. Okay, okay. The other one is through air. Okay, air or gas. Okay, and that's convection. Okay, the other one is through a liquid. Okay, okay, and give me a sec. Okay, through a liquid. Okay, and I don't remember what the name for this one is. And then the fourth one is through a vacuum, and that's mainly how he travels through the vacuum of space, and that's through IR radiation, infrared radiation. Okay, please excuse this miswriting and all. I still haven't gotten used to using this thing, but it's through infrared radiation. Okay, and there's something else that kind of behaves in the similar way, and that's sound. But the thing about sound is that sound doesn't have this. It doesn't have this at all. Okay, sound can travel through solids, through through liquids, not that efficiently, and through air, gas. That's how you're able to hear this. That's how we are able to hear this. But it doesn't have the ability to travel through a vacuum. So if you had something, for example, if you let's say, let me erase this. Okay, so like I was saying, if let's say you are here, okay, you're yelling as loud as you can, okay, and let's say you're in a bubble, considering that you have enough air to breathe in there, okay, and the outside, it's completely isolated. This here is a complete vacuum, and this area where you're standing is completely isolated from the walls of the outer container. In between, there's nothing but vacuum. Okay, even even if you yelled out the loudest, the people out here would not be able to hear you at all, because there's no way for sound to go through here in any way or form. Now, heat, on the other hand, is a different deal, because heat radiates through the form of infrared radiation. Okay, so now that I got that clear, um, we already covered temperature difference. Okay, we already covered temperature difference, which is your delta T. Um, Medium, which is your solid, the medium through solid, liquid, gas, and through vacuum. Okay, and the other point is, and it falls in this category also, is that you have to see how much specific heat capacity each material has. This mostly, actually, this applies to solid, liquids, and gases. Okay, because every solid, every liquid, and every gas has their specific heat capacity. For one example of gas, I guess you can include it in gas and liquid, is water, because of water vapor is the reason why the earth is able to retain some of its heat, not considering, of course, the internal heat from the planet. Because otherwise, what would happen is pretty much the heat, the heat from the earth, it would just pretty much dissipate out into the atmosphere, and it would not be able to retain. Okay, and this usually happens when there isn't that much humidity or an extremely low level of humidity. A lot of the heat tends to dissipate out into the air and out into space because there's nothing to retain it. And the reason why is that oxygen, okay, oxygen, O2, and nitrogen don't have a high enough specific heat capacity like, oh, let's say water. This is part of the reason why they use it on car radiators, because it has a high heat capacity. Another thing that has high heat capacity, and this is in the solid section, is steel. Okay, steel or iron. Okay, those have high heat capacity. But the problem with when considering heat sinks, the problem with using these is that yes, they absorb a lot of heat, but once these things heat up, they have trouble letting go some of the heat because they're able to retain so much heat, and that isn't something you want. You want something to be able to absorb heat, but also to dissipate it. And what better choice than aluminum itself? Okay, and that's where it falls into this medium aspect. Okay, and just to clear up how heat is able to transfer to solid, liquid, gases, and vacuum is because remember, it's IR radiation. Okay, through vacuums, IR radiation. Solid, liquid, gases is through the vibration of molecules. Okay, and the one I wanted to come to um, is surface area. Okay, S- surface area. Okay, surface area. Okay, and let me give you an example of how exactly this determines um, how much heat travels from point to point. Now, let's say there's a red hot plate. Okay, and let's say your dumbass decides to touch it for some odd reason or so. Okay, Okay, let's say your dumbass decides to touch it for some odd reason. Okay, and let me do a closer illustration. Okay, here's a red, and let's say here's your hand. Okay, which one do you think will burn you more? If you touch it with a fingertip or if you touch a whole hand? Okay, and the answer is your whole hand because there's more surface area for heat to travel. If you touch it only with your finger, that it's only your fingertip where it'll burn you. It'll hurt like hell, but it's only your fingertip that will burn you. And it's the same thing with um with with other objects. If uh if you have a hot object, okay, there's an aluminum bar, okay, and below you have a cold object, okay. Even though there's a high temperature difference here, it's not gonna travel as efficiently. This is of course ignoring the whole convection and radiation um, from the rest of the area between both objects. Is mainly gonna travel through this narrow cross section area, and it's not gonna be able to transfer heat as efficiently, rather than let's say that if you eliminated it and you put both of these plates together. Okay, so the question is, why do heat sinks look like this? Okay, and the reason why is because take a look at the heat sink and how it's shaped. If you notice how it's shaped like this. Okay, from one side, I'm gonna put four sides. That's side one, side two, side three, and side four. Okay, on the bottom side, it's like this. Okay, on the top side, it's like this. Okay, not much here. You would say, if anything, very little cross section area here from the top part. But if you look at from the sides, that's a different story. There's like this is just kind of a broad illustration of it. I'm not good at drawing this thing. If you look at it from the sides, okay, I'm not good at drawing, but anyway, if you look at the sides, and let me go ahead and draw this better. Okay, this is a rough illustration. Okay, if your heat sink looked just a square, a simple square, you will only get this surface area. However, if you have it like fins, like it shows here, you would pretty much have this as surface area, but you would also have the sides of each of the fins, which adds to the surface area. Okay, each of the fins individually. So when you add up the surface area from this, the surface area from these portions of each of the fins, the outer parts, and even the top part, then you have a much larger surface area. Okay, but anyway, I hope I explained everything clearly in this. I guess you can say call it a tutorial or so. But anyway, thank you guys for watching. Please like and subscribe or pledge to my Patreon, and I'll catch you guys next time.